Hello, welcome to another video in my series on management science, where we utilize Microsoft Excel to set up, model, and then solve simple, everyday business problems. Now, this problem is not really a new one. It is an extension of the previous problem I did. Now, if you remember, we had a high-end auto company called Merrari Motors located in Stuttgart, Germany. And in the United States, their major market is Los Angeles. However, the LA office has had a lot of recent turmoil, and no one there bothered to order any replacement parts. So customers were not able to get their cars repaired, to get their cars customized, or anything like that. So they had a real parts bind in the LA office. So the new LA manager called Stuttgart in Germany and basically said, we need replacement parts and we need them yesterday. So as managers in Stuttgart, it was our responsibility to figure out just how much product we can push through our distribution network. Because like any network system, it can only hold a certain capacity. So we needed to figure out, given all the routes the product could take, just how much we could be pushing through that network at any given time. And what we found out is that the flow of products through the network is maxed out at 150 units. That's all we could do. So our distribution pipes, if you want to think of it that way, just could not hold any more product. That was the absolute maximum we could push through. We weren't quite happy with that number. Our capacity in our network really limited us. So what we decided to do was add some nodes or some routes to our network to hopefully increase its capacity. And actually that is the point of this problem here. We're going to add some new distribution channels and see just how that will affect our maximum throughput in our distribution network. So here's what we decided to do. Now at the top you can see that we added a new origination node in Berlin. Merrari Motors had a second factory up in Berlin, but it mainly fed Northern Europe. But since Europeans aren't buying many high-end cars right now, they figured they could utilize part of that factory to manufacture parts and then send them on through the network out to the west coast of the U.S. Now, speaking of the U.S., if you look at the bottom of this list, we added a new destination node in Seattle. And we did that because we thought that if L.A. and or Seattle, because Seattle has a small market for Merrari cars, but if either city got into parts trouble in terms of not having enough parts, they could help each other out very quickly. It's much easier to get a part from Seattle to LA than from Stuttgart to LA. So we added a new destination node on the west coast. Now to facilitate that new route, we also added two transshipment nodes. The first one is in Hamburg and the second is in Boston. And when we add those four new nodes, this is what our network now looks like. So as you can see on the right hand side, the uppermost green circle, BE, stands for Berlin. And as we go along the top of our network, we have Berlin, then we have Hamburg, which is HA, BN, which is Boston, and then SE, which is Seattle. So those four nodes are brand new to our network. Now they will connect to other nodes, of course, and those connections themselves will have capacity constraints. But we're hoping that the overall network, with one more origination, two more transshipment nodes, and one more destination node, that overall it will allow us to push more product through our network. So adding those four new nodes changes our spreadsheet just a little bit. It's basically the same format, but we have new arcs or new shipment paths on the left-hand side, so our list is a bit longer. Now over on the right-hand side under nodes, you will see Berlin there in green, and then you will see Hamburg and Boston in yellow. Those are our two transshipment nodes. And then at the bottom, you will see Seattle there in red. So all of our paths are on the left-hand side, just like the previous problem, and our nodes are on the right-hand side. Now notice, since Hamburg and Boston are transshipment nodes, they fall within our supply-demand constraint of 0, because all the product going into Hamburg and Boston must go out. They're not warehouses. They're just distribution centers where things are divvied up and then sent on their way. Now, to put this in a more concrete form, I tried to think of a few real-world, current, modern examples of distribution capacity constraints that we have every day. And I came up with 4, at least off the top of my head. Now, the first capacity maximized network I could think of is the U.S. highway system. Any of us that have sat in rush hour traffic can attest to the capacity limits of the U.S. interstate system. Now, this map is a density map. It's a flow map. And it's even, at this point, about 14 years old. But the thicker the red, the higher the capacity on that system of roads. So you can see the eastern half of the U.S. is really working at its full capacity. And then along the west coast, all the major cities up and down the west coast, California in particular, have a high amount of capacity. In this case, I think it's actually truck volume. But the network actually exposes where the cities are. So you can see where Dallas is. You can see where Atlanta is. You can see where Chicago, New York, and LA are. So this is just like our shipment network, that along each path we can only hold so much product. And actually, if you think about it, this actually is pretty close, because if we're shipping product along roadways, this represents just how much product we could ship in a reasonable amount of time. So anyway, the interstate highway system is definitely an example of maximized network capacity. Now, the next example I could think of was the system of pipelines that moves petroleum products around the United States. So in this map, you have crude oil pipelines, you have natural gas pipelines, and things like that. Of course, they are concentrated in Texas and Oklahoma, where a good deal, if not the vast majority, of petroleum drilling occurs in the United States. Then, of course, you have along the coasts and other ports, you have pipelines leading to those, because those are distribution centers that load up tankers and maybe take the petroleum products elsewhere. And of course, this has been an issue in the news lately about whether or not we should or should not add a pipeline down the middle of the United States, and what are the benefits and costs of that. But petroleum pipelines are definitely a distribution network in terms of flow capacity. The internet is definitely a capacity-constrained system. If you have a smartphone and you live in a large city, especially like New York or something, you know about the constraints of the bandwidth in the network. Your ISP, your internet service provider, actually may be throttling the capacity on how much data you can download per month. So the internet is definitely a network that is limited by capacity in certain areas. And actually in this graphic, if you look below, the color-coded legend down below will actually show you how it corresponds to the lines on the map. Capacity in terabytes a second. So from red to orange, then to gray. So that's exactly like the shipment paths in our distribution network for the auto company. And then the final one I could think of is if you live in California or are familiar with the water system in California, there is a vast network of aqueducts that flow through California. And those aqueducts move water from the eastern part of the state over to the western part of the state where the major cities are. And many cities in California just would not exist in their current form if California did not have a vast system or network of aqueducts to move water. And of course, as you can see from this photo, the aqueducts can only hold so much water before they overflow. So this is definitely a capacity limited system, and of course there are mechanisms in place to direct water from aqueduct to aqueduct depending on the rainfall patterns and stuff like that. So the interstate highway system, the petroleum pipeline system, the internet network system, and the aqueduct system are all capacity constrained networks that in one way or another we experience every day. Before we actually jump into Excel to put in our data and solve our problem, we're going to continue the practice of making a diagram of our network before we actually go into Excel. So what we're going to do now is actually draw out our network in a drawing program so we can actually see what it looks like. And then after we do our diagram, we will jump back into Excel, enter our data, and use the solver to find the maximum flow in our new network. So here is our new distribution network. Again, we have added Berlin over on the top right, Hamburg at the top, center right, Boston, and then Seattle. So those four along the top are our new nodes. Now the first step in any diagram like this is to go ahead and draw in our arcs or our shipment lanes. So I will go ahead and just start one real quick. There we go. Now again, I'm not going to sit here and leave the video running while I draw all these in. So I'll go ahead and pause it now, and then I'll restart the video when I'm done drawing those in. Okay, so here are all of our distribution arcs or our shipping lanes. Now I've not put an arrow at the end of each one, but I have put a large arrow at the top just to remind you that these are directional. We are only shipping in one direction. That's what makes it an arc. Now as you can see, we have several shipping arcs. We have 16 actually in total. So this problem is going to be more complex because adding those 4 new nodes led to many more shipping arcs. Now the next step in our diagram is to actually draw in the capacity for each arc. So again, I'm going to go ahead and pause the video. I will draw in the capacity for each arc, and then I will restart the video. So here is our expanded distribution network. Now I've gone ahead and typed in the capacity for each arc. So you can see that the Berlin, Hamburg, Boston, Seattle pathway seems to add quite a bit of capacity to our network. But of course it's going to be the numbers that prove that out or not. So we're going to have to wait and do the actual problem to see just how much it adds, if any. Then I've gone ahead and listed the actual paths over there on the right hand side, the from and to, and that's just a list of all the pairs in our diagram. So now we have a good visual of our new distribution network. Let's go ahead and go back into Excel and find out the maximum amount of product we can push through this network. So here we are back in Excel, and we're going to go ahead and solve our problem. Now, I'm not going to go into a lot of depth about the spreadsheet because I did that in the previous version of this problem. Everything is pretty much the same. The formulas work the same, our final answer is the same, the constraints in the solver are the same, so I'm not going to go ahead and re-explain all that. Now, just keep in mind that over on the right hand side, in our supply-demand constraint, that Hamburg and Boston are going to be 0 because they are transshipment nodes, and then Berlin would be a new origination node, and Seattle would be a new termination node. So let's go ahead and type in the couple of formulas we need, and then we'll solve it. So we're going to go up to the top of the net flow column, and this will be the sum if formula again, so equals sum if, okay, from H4 ship. And again, the cell regions are already named in this spreadsheet, just like the previous problem. Minus sum if to H4 ship. So this formula is just figuring out the net flow into or out of a node. So all the transshipment nodes are going to have to be 0. This makes sure that the same amount is going out as is coming in. But then for Stuttgart, Berlin, we're going to have positive outflow or net flow. And then for LA and Seattle, we should have negative flow, which means they're taking goods out of the network. So let's go ahead and enter. And again, we do not have any figures for ship yet because that's what Excel is going to find for us. So these values are going to be 0 for now. So let's go ahead and drag down. And they are all 0. Now our maximum flow, in this case, is not just one cell. It will be what comes out of Stuttgart and Berlin, because those are both origination nodes. So this is simply equals the sum of those two cells. So believe it or not, that is it. As far as formulas go, that's all we have in our problem. Now we're going to go ahead and open up the solver to have Excel find the values in the ship column. So we'll go to Data, Solver, open it up. And remember, our objective is the same thing, max flow. We want to maximize that, so we click the max radio button. By changing the values in ship, which is the light blue column next to capacity, and we do have some constraints, so we'll go ahead and add those. Remember, our first constraint is that the cells, the transshipment cell net flow, has to be 0. So this column should actually be equal signs. So I will actually change that in the downloadable file, so that will be correct. But for our purposes here, it's not anything functional. It just lets us know that it's less than or equal to. Anyway, so we need the cells next to the blue to be equal to 0, which we have called supply demand. So supply demand is just the region of blue cells. So the cells next to it must be equal to 0. So we'll go ahead and click OK. And then we have one more constraint, which is the biggie, so to say, and that is that our shipment capacity or shipment amounts cannot exceed the capacity. So ship must be less than or equal to capacity. Click OK. So we'll just double check everything. Max flow maximized by changing the ship cells subject to the constraints that the transshipment cells must be equal to 0 and our shipping quantities must be less than or equal to the capacity in each lane. Now we always check to make sure our make unconstrained variables non-negative is checked, which it is. Our solving method is simplex LP, so we'll select that and we'll go ahead and click solve. Alright, and solver found a solution. All constraints have been met. Do we want to keep our solution? Yes, we do. We'll click OK. Let's take a look at what we have here. If we look in the ship column here, we'll see that all of our shipment lanes are either at or below their capacity, which is good because that's the constraint we put on our problem. We cannot overfill our capacity. Now down below that, you will see that our maximum flow is now 220 units. Here's the sort of solution to our problem. By adding Berlin as an origination, Hamburg and Boston as transshipment nodes, and Seattle as a destination node, we have increased our maximum product flow from 150 to 220. So we have increased it by 70 units, which is what? About almost a 50% increase in our flow just by adding those 4 nodes. So that's quite an increase. Now if we go up to our nodes net flow supply demand, you'll notice that we have 150 units coming out of Stuttgart. We have 70 units coming out of Berlin. So that's 220. Now if we go down to the very bottom, Los Angeles is taking 160 items out of the network, and Seattle is taking the other 60, which also adds up to 220. So you can see that our combined outflow is 220. our combined destination cities also equal 220. So that's really the end of this problem. All of our capacity constraints are met in our shipping lanes, and our net flow out into the network is the same as the net inflow from the network when they reach their destination. So I hope you've learned a lot, and I look forward to seeing you next time.